Hello everyone, this is Chen from Tohoku University in Japan. It's my pleasure to introduce my topic to you about the frequency and the Q-factor match to assess dual-mass resonator. And the first page shows the contents. The first part is about the research background, and then I will introduce some frequency and Q-factor tuning methods to you. Next, I will also introduce the simulation and the experimental results about our proposed tuning fork resonator. The last part is conclusion and acknowledgement. So for the first part is the research background. We believe many people work on the next generation application like the automotive and the robotic. And this kind of new technology require one of the important components, the gyroscope, the high precision gyroscope for the navigation and also the orientation detection. And the MEMS gyroscope can be one of the candidates for the high performance gyroscope. But its performance should be increased largely to achieve the requirement from the navigation. So FM and RIG MEMS gyroscope can be the candidate for the high performance MEMS gyroscope because they are insensitive to the temperature and has very stable scale vector and wide operation bandwidth. But this kind of gyroscope, the FM gyroscope, requires a highly symmetric resonator with frequency and Q-factor matching to decrease the interference of the degenerating modes and the sensing error. Therefore, many researchers work on the Q frequencies and the Q-factor tuning. So in this part, so we can modify the frequencies of the resonator by trimming the suspension spring of the resonator and also deposit the mass to the ring resonator. So in these two research. Another method, we can also add the DC bias to the sensing electrode to electrostatically softening the stiffness of the resonator. For the Q-factor tuning methods, so here I showed two of the methods. One is electrical damping turning, and also another one is the enclosed turning. The researcher used the COM drive and also the DC bias to turn the electrical damping of the resonator to turn the Q-factor. And in this research, so we control the motion between two outer mass to control the anchor loss and also adjust the Q-factor of the resonator. And in this research, so we propose a new mechanism to turn the Q-factor related to the squeeze field damping. We propose a tuning fork resonator, but it's also integrated with an actual inner mass structure for the squeeze field damping turning. So at the beginning, this after the fabrication, a stiffening mismatch exists between two outer mass, but the motion between two outer mass is kept balanced because of the inner mass. Therefore, the inner mass also keep static because of the balanced motion. But when we add the DC bias to the C2 electrode here, so we can soften the K3 stiffness. The motion imbalance between two outer mass occurs, so which induces the vibration of the inner mass and also the increase of the squeeze field damping. Therefore, we can control the Q-factor of one axis by changing the DC bias on the C2. So for the fabricated device, here is the design parameter of the device. The inner mass should be 1 order smaller than the proof mass to keep the small footprint of the device as 5.3 millimeter. And suspension stiffness, inner stiffness, coupling stiffness should be carefully designed to avoid the strong mode coupling between the antiphase mode and also the in-phase mode. For the experiment characterization. So we firstly use a large range frequency swapping to review. There are three modes in each axis, in x-axis and also the y-axis, which match well with the simulation results. And the second mode should be the antiphase mode, also the designed mode in this research. So when we look into the S mode, the antiphase mode along x-axis and also the Y mode, the antiphase mode along the y-axis, so we can see their frequencies and also the Q factor after fabrication in 70 Pascal environment. And by this, by their as-fabricated frequency and Q factor, we can find out the as-fabricated frequency mismatch as 5% and also the initial Q factor mismatch as 7.7%. So our purpose in this research is to cancel, to compensate this two mismatch. We also do the simulation to check the Q factor of the device. So the circle point in this figure show the measured Q factor, and the dashed line show the simulation value by the simulation tool developed by the Polytech Milano. So in this simulation, we consider three kinds of air damping, including the parallel plate, photo spring, and also the actuating combs. And we can see the simulation, the experimental results match well with the simulation tool. So we can know during 100 Pascal and also 200 Pascal, the Q factor of this device is mainly constrained by the air damping. And that's so our slide show the resonant motion captured by the Polytech, and we can see the antiphase mode in this movie, and so which show the upside vibration between the this is the outer plane and this is the inner mass. So they move in upside direction as the antiphase mode. And when we add the DC bias on the inner electrode, maybe this one electrode, so we can see the mode motion change, the unbalanced motion between the outer frame and also the inner mass occurs. And on the other hand, the inner mass also started to vibrate. So we can, so in this movie, we can prove that the DC bias on the inner electrode can change the mode motion of this device. And let's now show the inner DC bias effect on the Q factor. So this curve shows the frequency response under different inner bias. We can see, so with the increase of the inner bias, the frequency shift and also the Q factor decrease gradually. And compared with the initial case, the case under the 27 Wolf DC bias, the frequencies of the interface mode drop by 2.6 Hertz, and also the Q factor of the antiphase mode decrease from 5.2 thousand to 4.1 thousand. So we also confirmed the Q factor turning under different pressure as 3 Pascal, 10 Pascal, and 70 Pascal. So we can observe the Q factor turning by the inner turning bias in different pressure. And the dashed line show the theoretical model we built. So we also confirmed the experimental results match well with the theoretical model. And this last slide show the frequency and Q factor matching between S mode and Y mode in the experiment. So firstly, we applied the DC bias on the sensing electrode of inner mass and also the outer frame to simultaneously electrostatic soften the K1 and K3. So we can make the frequency of the SS to approach the frequencies of of the SSS. And under 82.16 Wolf on the sensing inertial, the frequency difference between the YSS mode and also the SS modes was about 2 Hz. And after this one, we add another, so extra 30 Wolf on the inner inertial, so it will cause a small shift of the frequencies on the Y mode, but it also will cause the degrees of the Q factor to match the Q factor of the S mode. So in this figure, we can finally see the frequency matching and the Q factor matching between S mode and Y mode was achieved. For the conclusion, so we successfully validate the high turning capacity of the proposed 2SS to dual-mass resonator. And also the measured Q factor in different patterns match well with the simulation value. The theoretical model of the Q factor turning agree well with the experimental results, and the frequency match under 10 ppm, Q factor match under 650 ppm were achieved. And that's all. So this is acknowledgement. We acknowledge the support from NATO and also the JSPS project. Thank you very much for your attention. If you have any other question, please do not hesitate to let me know.